Yes. Hello, everyone. Was waiting for everyone to join
Good morning, ma'am.
so that we can complete DNF block in this session. Fine. Can we start our discussion right now? Is it fine?
Yes.
Very good morning. I cannot hear you, but I can just read the chats. Can you hear me? I've not shared the screen that's there. Other than that, you can hear me. Okay, fine. And now you can see the screen also, right? Fine. Okay. Such a lovely color and a very important compound from the NEAT viewpoint. Potassium dichromate, K2Cr2O7. Let's look into its preparation. I think so now we can start, right? And then people slowly join, let them check the recording and make up the remaining. So preparation. Dichromates are generally prepared from chromate. And first we should take chromite ore. Chromite ore is FeO.Cr2O3. FeCr2O4 is basically FeO.Cr2O3. When that is made to react with sodium carbonate and O2, and FeCr2O4 is made to react with sodium carbonate in the presence of oxygen. What we get is Na2CrO4, Fe2O3, CO2. Tell me what is the formula of chromate ion? What is the hybridization of chromium there? Chromate ion, chalo, I'll write. This is chromate ion. Yes. A 2 minus. Atika, 2 minus. Rest all fine. So now what should be the hybridization of chromium here? One till you people give me this answer. Chromate to dichromate. You have to add acid. Both chromate and dichromate have chromium in the plus 6 state. So let's write CrO4 2 minus X plus 4 into minus 2 is minus 2. Minus 2 plus 8 plus 6. Similarly, Cr2O7. What is CrO3 called? It can be called as an anhydride of chromic acid. Chromic anhydride. I'll tell. So H2CrO4, in which Cr is plus 6, is known as chromic acid. Huh. When it loses a water, CrO3, what we get is chromic anhydride. I told you the anhydride and the acid will always have the same oxidation number. Fine. Well and good. Now here, this is also 2 minus. 2x plus 7 into minus 2 is minus 2. X comes out to be plus 6. Yes. So chromate and dichromate both are plus 6. So when chromate becomes dichromate, it's not a redox reaction. Just remember that. By the way, if this slide is over, we can get to the next one. Knowingly, I was waiting here for some time. In case someone joins, they can like listen from the beginning. Yes. So this chromite ore. Okay. This chromite ore in the presence of Na2CO3 and O2 gives you chromate, sodium chromate. Chromate in acidic medium gives you dichromate. It's not a redox reaction because both have plus 6 oxidation number. Chromate in acidic medium, dichromate. So the yellow solution of, yeah, sodium chromate yellow color is acidified with H2SO4 to give orange colored dichromate. So yellow to orange. Everyone? So now you have got dichromate. Sodium dichromate is much more soluble than potassium dichromate. Fine. So when you have sodium dichromate, add HCl, add KCl to it, and you get orange colored crystals. This is orange solution because sodium salts are soluble in water. The solubility of potassium dichromate is quite less than that of sodium dichromate. So, but you need potassium dichromate, right? So what will you do? You will add KCl. By double displacement, you get orange crystals of potassium dichromate. Yes, as I mentioned. So chromate to dichromate, acidic medium. Dichromate to chromate, basic medium. Dichromate to chromate, basic medium. Fine, everyone. Once again, let's see how much we remember. So chromite ore will be treated with Na2CO3 and O2 so that yellow colored sodium chromate will be formed. Now, chromate to dichromate, that is possible in acidic medium. So you'll add acid such that so sodium chromate upon acidification will produce what chromate? I'm sorry, what dichromate? Sodium dichromate. Sodium dichromate is relatively soluble and you get an orange solution and your purpose is not to prepare sodium dichromate. Your purpose is to prepare potassium dichromate solution. So what will happen? Sodium dichromate solution will be treated with KCl, double displacement, you get orange colored crystals of potassium dichromate. And from dichromate, if you want to go back to chromate, that will take place in basic medium. Fine, everyone clear? So it should get registered here. Correct? Chromite ore with Na2CO3 and O2, sodium chromate, yellow solution. Acidification will produce yellow solution of sodium dichromate, which by double displacement with KCl produces orange crystals of potassium dichromate. So chromate to dichromate, acidification, dichromate to chromate. You should add a base. So yes, so I'd ask this question about the hybridization of chromium. I didn't draw again because I know it will be here. So what will happen is, as you can clearly see, this is sp3 hybridized tetrahedral. Yes, sp3, yes. What about dichromate? There's a bridging oxygen, we understand, but this also should be sp3 only, no, individually if you look into. But yes, since it's Cr2O7 2 minus, there's a bridging oxygen in between them. Fine. The structures of chromate and dichromate ion both have chromium in plastic state. By the way, chromium in plastic state. What is the electronic configuration of chromium? We should definitely once look into. It has 6 valence electrons, and due to half-filled configuration, yesterday only we started D block, so it's really 5 4s1. So here what should happen is chromium should lose all its valence electron to become plus 6. Yes. So chromium, you have nothing more to lose. You can only act as oxidizing or reducing agent. Help me out. Very good. Good going, all of you. Yes. As we just now mentioned, oxidizing property. So what happens is chromium in dichromate is plus 6. When it acts as an oxidizing agent, it gets reduced to chromium in plus 3 state. So this chromium plus 3. Balance it, you have to put a 2 here. Why? Because the element which is undergoing a change in oxidation number, it should be balanced in either sides. So that's balanced? Yes, it is. So now let's see. 1 chromium plus 6. So chromium which is undergoing a change in oxidation number, I repeat, should be balanced at both ends. Here also, there are 2 chromium atoms, so I will put a 2 here. So 1 chromium is plus 6, 2 chromium is plus 12. 1 chromium is plus 3, 2 chromiums are plus 6. So plus 12 and plus 6, the difference is 6. Loss or gain? Of course, we are talking about gain because oxidizing agents get reduced. So here basically 6 electrons should be gained by Cr2O7 2 minus to form 2Cr3 plus. Now what will happen? We'll write it here. Cr2O7 minus plus 6 electrons gives 2Cr3 plus. Acidic medium. This N factor of dichromate is 6 in acidic medium. To balance the oxygens, I'll put here 7 water. And double of 7 is 14 H plus on the side. So that the hydrogens which you have put here is balanced. So students, as you know in your own way, Sir has taught you the redox balancing and all. I hope you understood that why it's 6. Because 1 chromium is plus 6, 2 chromium is plus 12. 1 chromium is plus 3, 2 chromium is plus 6. So the over basically 6 electrons should be gained when Cr3 plus is formed because 2 Cr3 plus is formed from Cr2O7 2 minus. You have to put here 2, then only it's balanced. Yes. So now for balancing oxygen, 7 water needs to be put here, and to balance the hydrogens because it's acidic medium, 14H plus here. This is the equation and this is the reason for this. Yes. So just now as we discussed, potassium dichromate is a very strong oxidizing agent. It will oxidize I minus into I2. It will oxidize others means what? It will make others lose electrons minus 1 to 0. So dichromate is oxidizing iodide into iodine, Sn2 plus into Sn4 plus, iodide into iodine, Sn2 plus into Sn4 plus, I am sorry, Fe2 plus into Fe3 plus, sulfur from minus 2, I mean sulfide to sulfur. It's basically bringing about oxidation of the other species, oxidation involves loss of electrons. So these are the cases where K2Cr2O7, maybe some more are also there as an oxidizing agent. Okay, so I'll tell you what they mean here. Let me explain. Cr2O7 2 minus produces 2 Cr3 plus. By gaining 6 electrons, you have understood very clearly. And to balance water, I'm sorry, oxygen, 7 water and 14 H plus. This you just now did. In case anyone has any doubts, I am ready to what permit. You can always unmute and ask, or you can type. In case I miss something in the chat, then you can let me know. Okay, I'm trying my best. If I miss something, you have asked something and I've not seen the chats, let me know. So this is getting reduced. So what is getting oxidized then? So dichromate can oxidize Fe2 plus to Fe3 plus. One electron is lost in this process. It's not possible one electron is lost and 6 electrons are gained. So what should we do here? The second equation should be multiplied throughout by 6. And we get Cr2O7 2 minus 14H plus 6 Fe2 plus, giving 2 Cr3 plus 6 Fe3 plus and 7 water. Followed everyone? Any doubts? So since Fe2 plus to Fe3 plus is only a 1 electron loss, 1 electron loss and 6 electron gain. No, to equalize the number of electrons lost and gain, I have cross multiplied and I've got this. So in this way, the other equation needs to be taken care of when you have to go to redox balancing. Otherwise, in inorganic, iodide to iodine, you should know iodide to iodine, SN 2 plus to 4 plus, sulfide, H2S means sulfide to sulfur, Fe2 plus to 3 plus, as I just now mentioned. Fine. Effect of heating. Dichromate gives you chromate and chromium trioxide. CrO3 is chromic anhydride, someone asked. Nandana, I think so, yes. But here, mark it, remember it, it's potassium dichromate on heating giving potassium chromate plus Cr2O3 plus O2. Yes, when we go for titrations, K2Cr2O7 is preferred over Na2Cr2O7 because what is hygroscopic? What do you mean by an hygroscopic substance? Something which can absorb water without dissolving in it. Water absorption capacity. There are two things. One absorbs water deliquescent like NaCl, salts. They'll absorb water and they'll become sticky. But here, glycerin will absorb water but will not dissolve in it. Very good. Oh my God. Holy season, and why should I miss this? Purple KMNO4. Students, when KMNO4 is converted into Mn2 plus, the purple color changes to dash. Purple or pink, whatever, dark pink, purple. Boys, everything is the same, you know. We'll look very specific. Magenta would not be the correct. Purple or dark pink, anything is fine. When KMNO4 is acting as an oxidizing agent in acidic medium, Mn plus 7 gets converted into Mn plus 2. No, colorless, not green or red, orange or something. Purple or dark pink to colorless. And when? This means I have to tell you that when this thing happens, This becomes orange to green. This one orange to green. The other one, this pink or dark purple to purple or dark pink, purple or dark pink to colorless. All right. KMNO4. Let's welcome KMNO4 first. A very, very strong oxidizing agent where manganese is present in its highest possible oxidation state, plus 7. Which element can exhibit plus 8 oxidation state? Yesterday we learned. Anyone will do? Anyone answer? Chats like which one can exhibit? Osmium. Correct. Osmium can exhibit plus 8 oxidation number. Let's talk about the preparation of KMNO4. Pyrrolosite, MnO2, when it's fused with an alkali in the presence of O2, gives us, this is by the way, potassium manganate. Pyrrolosite, MnO2. It's treated with an alkali metal hydroxide, KOH, NOH, anything will do. And an oxidizing agent, okay, like KNO3. But I can directly write O2 here because oxidizing agent will supply oxygen. So pyrrolosite in alkaline medium with an alkali metal hydroxide, be careful, huh? Along with an oxidizing agent will produce, this is potassium manganate. What is it? Potassium manganate. So I'll write potassium manganate as K2MnO4. I write it again and MnO4 2 minus ion manganate ion. What is the oxidation number of manganese here? What is its color? Written here green, dark green. This dark green manganate, not permanganate, manganate will disproportionate in acidic medium. So plus 6 will disproportionate into plus 7 and plus 2. I'm sorry, plus 4. Manganate will disproportionate into permanganate and MnO2. Dark green, very good. And we got what we required. It's dark pink, purple, anything will do. Both are accepted. Fine. So ultimately, what did we do? We took pyrrolosite, alkaline medium with the alkali metal hydroxide in the presence of air or oxygen. Will give us potassium manganate, which is dark green in color, in acidic medium when it disproportionates. I get purple colored permanganate and I'm happy. Along with that, MnO2 is produced because it's disproportionation, but this much only makes me sufficiently happy. Know this MnO2 is also obtained. This one we learned. In acidic medium, it disproportionates into KMNO4 and MnO2. Know that in the presence of O3, which is an oxidizing agent, it gives KMNO4 and O2. I get KMNO4, no. That's it. With chlorine, important students, K2Cr2O7 and KMNO4. As much information, preparation, structure, properties, try to not miss out these very important topics. With chlorine, you get KMNO4 and KCl. Electric arc in the presence of oxygen, KMNO4. It's oxidized, yeah, plus 6 to plus 7 means it's oxidation. Not only this, with ozone, with chlorine, electric oxidation, everything gives us dark pink or purple colored KMNO4. Industrial method, fine. This, otherwise, from where will we get this electric arc and all those setup, right? Industrial method. K2MnO4, we just now saw it's green in strongly basic medium, and it's stable also. In basic medium, it's stable, dark green in color. In acidic medium, it's not stable. Uh, one second. Huh? One second. It is proportionates, giving you KMnO4 and MnO2 in acidic medium. Yes. It's a purple colored crystalline compound. It's an oxidizing, it's a very strong oxidizing agent. By the way, it can only act as an oxidizing agent, and it can itself get reduced into Mn2 plus. One second, I'll just check if this information is given in other slides, who will write again, right? Otherwise, I will write once. One second. Mang mm, one second. The next slide. Wait, I'll come back to this. What I'm trying to write, I'll tell you. Wait. MnO4 minus permanganate. MnO minus double bondo, double bondo, double bondo. MnO4 2 minus. Mn double bondo minus 1 minus 1. And what about this unpaired electron? We have to justify. Let's do it. Mn is argon 3d5 4s2. Mn plus 7 has no problem. Argon configuration. So when it bonds with oxygen, basically MnO4 minus, MnO minus, double bondo, double bondo, double bondo. MnO4 minus. Mn plus 6 should be argon 3d1. Everyone agrees? 6 electrons are lost. So first it's lost from 4s and then from 3d. So 1 3d, 1 electron will be there. And hence, it will have an unpaired electron. MnO4 2 minus means 2 of the oxygens are O minus, O minus. Rest to double bond O, double bond O. Fine. I'll draw. How does it look like? Mn O minus, O minus, double bond O in one of the unhybridized orbital. We'll keep this unpaired electron. Fine. Everyone, this one dark green, this one purple or dark pink. Very important. Tell me, help me recollect. I'll go back to that slide also. That was also not done. Tell me, K2Cr2O7 decomposes to give what major things? K2Cr2O7 decomposes giving K2CrO4. K2Cr2O7 decomposes giving K2CrO4 plus Cr2O3. These two are more important. Chromium, Cr2O3 plus K2CrO4. Yes, Cr2O3, Atika. Cr2O3 plus K2CrO4. This one, this gives K2MnO4 plus MnO2. Important. Anyways, we'll go back to this. So what it's trying to show here is, if I take a plus 2 salt, it gets reduced to the plus 7 state. Okay. It gets oxidized. Plus 2 to plus 7 is oxidation. So Mn plus 2 gets oxidized to the plus 7 state. And who does this oxidizing work? So peroxo disulfate is used as an oxidizing agent here, and it converts plus 2 to the plus 7 state. So peroxo disulfate is oxidizing Mn plus 2 to plus 7. Done. What method? Lamb method. Purple colored solid, it is oxidizing in nature and itself gets reduced to Mn2 plus. Yes, this one I was coming into. MnO4 minus in acidic medium becomes Mn plus 2. This Mn plus 2 is an auto catalyst, means say I titrate KMnO4 versus more salt or oxalic acid. When the reaction starts and a bit of di- permanganate starts getting converted into Mn2 plus. Once Mn2 plus forms, the rate of the reaction increases because this Mn2 plus acts as a self catalyst or auto catalyst, means you titrate or you make KMnO4 react with oxalic acid in acidic medium. You will see that initially the reaction is very slow, and slowly when Mn2 plus is formed, one of the product itself activates or initiates the rate of reaction or increases the rate of reaction. So Mn2 plus, you are acting as an auto catalyst. You're increasing the rate of the reaction, and you should not forget that the end factor of this reaction is 5 in acidic medium. The next thing is I have to put here 4 water and 8H plus and 5 electron gain. So MnO4 minus gets converted into Mn2 plus with a 5 electron gain in acidic medium, so 4 water and 8H plus. Correct me if I'm wrong. Check. I'm also checking. So acidic medium, N factor of KMnO4 is 5 because it gets converted into Mn plus. So this is important for redox. If it is neutral or weakly basic medium, so KMnO4, N factor, acidic medium, 5. Neutral or weakly basic medium. Who will help me? Very good. And last one, with strongly alkaline medium, strongly basic medium. Wow, good. So KMnO4 decomposes to give K2MnO4, MnO2, and O2 is okay. These are the two main products. So this is nothing but disproportionation. From plus 7 to plus 6, and disproportionation is the right term. No, na? Because here to here is also gain. It gains here also, it here also. Can't be called as disproportionation, but decomposition can be called. So KMnO4 gives K2MnO4 and MnO2. In case you're thinking why I'm repeating so many times, because a lot of stuffs to remember in case someone is not so much ready with the things, at least after the class or during the class it should like get registered. That's the only reason. Green color is due to manganate. Green color because of the presence of unpaired electron. But why should KMnO4 be colored then? It doesn't contain any unpaired electron. Huh. K2MnO4 we can understand paramagnetic, there's an unpaired electron, green in color, everything I can understand. But I don't understand for KMNO4. Mn is plus 7. Any idea? Have you heard of anything earlier when you have studied? It's colored, and not only KMNO4. KMNO4 and K2Cr2O7, there also chromium is plus 6. No, no unpaired electron. Why still they are colored? Because it's not due to DD transition. Formation of charge or something I'm getting in the chats. Let's see. In spite of ligand transfer electron. Okay. Yes. Formation of charge transfer complexes. This line would be good enough. No more details they ask. And need to still they don't ask. So because the there's some homo-lumo concept. Homo means highest occupied molecular orbital and lowest unoccupied molecular orbital. Okay, leave it. So they are colored due to the formation of charge transfer complexes, not due to DD transition. This will do. Very good that some of you are aware about that. Now it's a very strong oxidizing agent. I know it can only act as an oxidizing agent. It will oxidize oxalates, this oxalate to CO2. So oxalates have carbon in the plus 3 state. Oxalates will be oxidized to CO2. Fe2 plus to Fe3 plus. Understood. Nitrite to nitrate. Plus 3 to plus 5. Minus 1 to 0. All these things are brought about by what? KMNO4. It's a very, very strong oxidizing agent. Acidified KMNO4. Students, do you remember some reactions of acidified? Okay, chalo, let me ask you one. Not much. Can be an alkaline medium also here, not a problem. I have KMNO4. What will happen? No, no, it's not cold dilute. This will convert it. Here it will act as a strong oxidizing agent. Be as your reagent you want. Wait. This is alpha hydrogen with respect to the benzene ring. Not one, three alpha hydrogens are there. Requirement is only one. If only one alpha hydrogen is there with respect to the benzene ring, then KMNO4 in acidic medium heating, drastic conditions, will oxidize it to benzoic acid. And what you people are saying is this. Wait. Here, KMNO4 is oxidizing iodide to iodine, 2 plus to 3 plus, iodide to iodine. These things you know, huh? Well, let me tell you then. Suppose I have this alkene. Cold dilute means 1% dilute. Alkaline KMNO4 solution is known as Bayer's reagent. What it will do? Benzoic acid, I got an answer. Very good for the previous one. This one, two OH groups will be added. That also from the same site. Two OH groups will be added from the same site. Syn hydroxylation. This is the job of BS reagent, which is cold dilute alkaline solution of KMNO4. Oxalates means carbon in the plus 3, plus 4. Any doubts anytime you can ask either of us. Hydrogen sulfide Means S2 minus is converted into S0. Sulfurous acid means sulfur in the plus 4 state to plus 6. Oxidation again. Nitrite, sorry, plus 3. To more stable, nitrate plus 5. Self indicator, yes. This I was going to tell you. KMNO4 or permanganate is like purple or dark pink. Mostly you'll see that you're carrying out reactions in acidic medium. And when Mn2 plus is produced, it's colorless. So this change will indicate the completion of the reaction. So dark purple colored KMNO4, it's turning colorless. This color change, you don't need to add any indicator. I'll tell you a little bit in detail. If you want, I can tell you. Say for example, I have here, if you want, then only let me know. One line, huh? It will be not disturbing your like syllabus completion thing, and I can provide you some information also. So I'll take little warm solution of oxalic acid here, students, because oxalic acid has covalent bonding between carbon oxygen. So covalent bonds are not so easy to break or decompose in or break in aqueous medium. So I'll take little warm, some 60-70 degree. I'll heat this oxalic acid solution. Then oxalic acid is a weak acid. It's an acid, but right now here it will be acting as a reducing agent. For acidic medium, I'll add some dilute H2SO4. This will be taking place in that. This is conical flask. I have to draw one conical flask. Mm, chalo. You please manage with this. Now what happens is here. In the burette you will have KMNO4. Will not add any indicator. So the moment a drop of a little better, little more better I can draw. Huh? So purple colored KMNO4 falls here. In acidic medium, it acts as an oxidizing agent. Reducing agent is oxalic acid, and Mn2 plus is produced, which is colorless. So purple will be colorless. Purple will be colorless till the reaction goes on. When all the oxalic acid is consumed, purple can't be converted into colorless. Reducing agent is consumed. That time the colorless solution will turn light pink in color. Light pink, why not dark pink? I'll add a few drops. If you add more, it will turn dark pink. No, just add a drop or two extra. After the completion of the reaction, you will see pink remains pink, means there is no more reducing agent to convert it into colorless Mn2 plus. Endpoint is pale permanent pink. If the pink disappears, means it has converted into Mn2 plus. Correct? No? Anyone from here, Bangalore, like PU syllabus, they do it in the lab, right? This reaction must be knowing. Okay. Um, the endpoint is pale permanent pink color. You did it for CBSE also. School gas, yeah. This is a school experiment. There's a reason. Very common. But I don't know what is all. I teach only for this, so I remember in some of the colleges and all this thing is there. Okay. The endpoint, but pink dropping here, becoming colorless, Mn2 plus. This will continue till reducing agent is not exhausted. When the reducing agent is completely exhausted, then an extra drop of KMNO4 indicates completion of the reaction. When you treat it with concentrated H2SO4, Mn2O7, an explosive, is produced. Fine. Got some idea? Who is coming? F block. Ah, what a welcome. Inner transition elements. Here, the n minus 2 F subshell is successively filled. So the elements of F block don't have much space to be accommodated vertically, though they have similar properties. So the ones which will have similar properties should be accommodated vertically. No, no space here. So they are progressively like filled next to each other one by one, and placed at the below end of the periodic table towards the bottom. Like as if a class is completely filled, the chairs, tables, and some extra people, they've accommodated those students and asking them to sit on the floor. Correct? No? Like that it is. So a block lanthanides, actinides, 4F successively filled lanthanides, 5F successively filled actinides. Mostly the actinides are radioactive in nature. Yes, I should have asked this, but okay, since I've already clicked. Basically, they are an extension of group 3. Group 3. The first one, the scandium one. So, these are formal members of, say, for example, they make me sit in another room, but I study in class 4. They make me sit in class 5 for some reason for a while, whatever. But I'm formally a member of class 4 only. So these elements are formal members of group 3, and lanthanides, I don't know if it comes to the next point or not, doesn't matter, belongs to the 6th period. Actinides belong to 7th period, and both belong to group 3 of the periodic table. Okay. Inner transition metals can also be used. Instead of calling them as F block elements, we can call them as inner transition element. Why? Because it's the valence shell, penultimate shell, and anti-penultimate shell. So this shell is being successively filled. We'll look into its electronic configuration, we'll understand it better. So there are two series, lanthanides and actinides. So 14 elements form lanthanum, or like lanthanide series. Why this name? Because all 14 resemble very closely in property with which element? Element with atomic number 57, lanthanum. So because lanthanum closely resembles the lanthanides, so that's the reason it is known as lanthanide series, in which the 4f orbital is being successively filled. Capacity of the lanthanide, like how many elements in lanthanides? 14. There are 14 elements. Sorry, this is the capacity of F is maximum 14. So 14 elements can be filled there. Similarly, 14 more in the actinides. 5F series. 14 elements follow actinium. And they are a member of actinide series. I don't think it's important to remember all the names. Symbol will also do. Correct, no? Cerium is okay. You want, if you can. What, you students, you remember all of them? Promethium is radioactive in nature, no? Do you remember all these names? The last minute I won't ask you to, in case you have not. The symbols at least. Symbols with their atomic numbers. Tell me. Okay. So cerium. No, ma'am, not remember. It's okay. Last minute. Only lanthanoids. Some says only lanthanoids. Fine. Last minute, what you can do is symbols with their atomic number would be good enough. European gadolinium. I'll tell you at least certain things we can do. Terbium, dysprosium. I generally go by DY, HO, TBGD, EU, PM, like that. SM. Last one. Now see. See all of them, then you'll understand better. First, we will take like 4F. We'll and 5D and 6S. What am I doing? I'll tell you. N L N plus L N L N plus L. According to the N plus L value, it should be 6S should be filled first. Then both has some N plus L value. Then the one which has lower N should be filled first. Will you agree with this? Yes. Aubau's principle, N plus L rule. This should be the way of filling. So everywhere whereas where 6S is okay, fine. 6S is completely filled. Are we justified? Yes. Next. After that, it enters 5D or 4F. Should be 4F and then 5D, but doesn't matter much because okay, no problem. First 4F, no. First 4F, then it should have been 4F too. Ideally, if you ask, it should be first 4F should be filled and then D, no. 4F and then 5D. See here 3 and then 0. This anomalous behavior can only be justified. So 6 is first one done. Then complete 4F and then 5D. No, but that's not happening. And this is what has been found out or whatever given to us for you and me for learning. We can justify with the fact that 4F and 5D. So remember for cerium, if possible all, europium and gadolinium because they have half filled F configuration. So 4F and 5D are or have very less difference in energy. Four F and 5D. They have very less difference in energy. So this kind of behavior is seen. So 6S filled first justified. 4F completely and 5D. That's not happening in all the places here, so I can justify. I'm happy here. It's easy to justify. First 4F and then 5D is empty. Here also, okay. These are good people following rules. Good, 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 good. But here understood. Just like chromium copper. The half-filled configuration is very, very stable. So here though in gadolinium, I do understand. And in cerium, I don't understand. Agreed, everyone?
Yes, ma'am.
Correct, no, all the places, see, I analyzed it in this way. When I saw this, the same, whatever I do self-analysis, the same I discuss. Like that, I'm So 6 is justified, and then 4F should be completely, and then it should come to 5D. Here it's understood because of half field configuration rather than 8 and 0, 7 and 1. Okay, I understand. In all these cases, also D is untouched because it should be touched only after F. That also I understand. Cerium, remember this. Easy? Anything else, you can always let me know. Understood. If D is kept vacant, understood. Understood everything. Why? Because 4F14 completely filled shell. No problem here. I should like, there's no doubt. After 4F14 is filled and then it's going to 5D1, no exception, no problem, right? According to me, if you have any doubt, you can ask. A lot of anomalous behavior is seen in actinides. Lanthanoids, some people don't know. You remember the name or the stuffs. It's okay. It's justified also. Except cerium, it's only the cerium thing. Fine, understood. Can we proceed? I don't see much irregularity. Only in that 4F7 and 5D1 instead of 4F8. Understood. Yes. Now, from if lanthanum and sorry, if cerium onwards, cerium to lutetium, they have similar properties as that of lanthanum. They should be placed under the same group. And what should happen? When what do you expect? They should be like placed one below the other in the group, no space, so they are just placed like this. A typical thing has been observed: a regular decrease in the radii from lanthanum to lutetium. And what's the reason? Lanthanide contraction. What is it? That when one by one the 4F is successively filled. Now understood why 4F is filled. It should be like 6S. Understood? Then 4F, except a few exceptions, very, very less. First 4F and then 5D, and then it should be like 6P if at all. Right now, nothing is there. The sequence 60. Okay, yes. So when 4F is being successively filled, because F has poor shielding ability, poor screening increases the effective nuclear charge. So what did I say? When we move across the lanthanide series from cerium to lutetium, you will see that the 4F orbital is being successively filled. F electrons having poor shielding ability will means they are there, but as if they are not there, will attract the valence electron very effectively, means that effective. So poor shielding of F electrons means the Z effective between the nucleus and the outermost electron increases, size decreases, and this is the basis of lanthanide or actinide contraction. Same logic. Fine. And the screening ability of F the least. SPDF. Decreasing shielding effect. See, a regular decrease. Consequence, as discussed yesterday, 3D to 4D, there is a quite increase. Large increase in size. 4D to 5D. The atomic radii, the size almost remains same or less difference. Small difference. Either almost same or very slight increase. Or maybe in some places slight decrease. I don't remember those values so imperfect. So not much difference in the values will do. Basic strength. You think no students lanthanum hydroxide, lutetium hydroxide. Think. I'm sorry. I'm sorry. The most common oxidation number of lanthanides is +3. So I correct myself. So it's La3 plus, which is large, Lu3 plus, which is quite small, much smaller. That's what we discussed in the lanthanide contraction. So what do you expect if something is small? I can think in various ways, but all comes to the same conclusion. If I think that hydroxide is a small anion, so small, more compatible. So Lu3 plus holds OH minus very strongly when it's effectively. High lattice energy, basic strength less. I have one more idea. One more idea. If I think that if the small cation has high polarizing power, so if I think this is a small cation as compared to the others, and it is high polarizing power and means greater covalent character, then there will be greater covalent character of LuOH whole thrice. If its covalent character is more, it will not dissociate easily. Covalent compounds will not be that soluble in aqueous polar solvent like water. It will not dissociate that effectively. It will not produce for basic strength to be sufficient. It should produce sufficient OH minus. No, this way also you can think. Small size, high polarizing power, greater covalent character will not be that effectively soluble in solvents like water. Otherwise, Lu3 plus small in size, OH minus is small anion. OH minus is considered always a small anion. Very good bonding they will have. They will attract each other effectively. Lattice energy will be high. Will not be again willing to give OH minus. The basic strength should decrease. Yes, there's a steady decrease in size. So lanthanum, 1 second. As I told you, the most common oxidation state is +3. They also show +4 and +2 oxidation state. So Ce in +4 oxidation state is a strong oxidizing agent. Why? Because Ce+4 thinks if I'm an oxidizing agent, I can get reduced to the +3 state easily. So Ce+4 exists, no doubt, but Ce in +4 state is a strong oxidizing agent. Eu2 plus, same reason. Everyone wants to go to the +3 state, the more common state in lanthanide. So +2, Eu+2 thinks if I should lose an electron and get oxidized to, I should lose an electron and get oxidized to Eu plus 3, +2 to +3. More stable state in lanthanides, a more common oxidation state. So I can do this by acting as a good reducing agent so they can get oxidized easily. YB2 plus is a reductant for the same reason. It should also, same, think of going to YB plus 3. So this is a good reductant. If anyone has to lose, it should be a good reducing agent. C plus 4 is a strong oxidant or oxidizing agent. Plus 4 wants to go to plus 3 by gaining. So it's a strong oxidizing agent. Plus 2 wants to become plus 3 by losing. So it's a good reducing agent. Important. Same reason. If it's plus 4, it will be an oxidant. Plus 2, it will be a good reductant. SM, like EU, can show both plus 2 and plus 3 states. Cerium, plus 3 and plus 4. I understand that a lot of facts are there, but see how the electronic configuration I said, except cerium, then you can, and gadolinium also. The remaining you can correlate. Try to remember the symbols and the atomic numbers also. Silvery white soft metals. Tarnishing means getting oxidized easily in air. Metallic structure, good conductors of heat as well as electricity. Students, color, as I was just now telling, is due to the presence of, see, if there's an unpaired electron, DD transitions will take place. If there's an unpaired F electron, FF transitions will take place, and you can observe color for those compounds. For K2, Cr2O7 and KMNO4, though I didn't give details because that much time we don't have. And without doing that also it will be like, okay, they don't ask details. Charge transfer complexes are formed. Metal to ligand, ligand to metal. Ligand, what is ligand? We'll learn today only in coordination compounds, next class. So that is the reason K2Cr2, KMNO4, they don't have d electrons at all. So metal to ligand, ligand to metal. Transfer of electrons, charge transfer complexes. In other cases, unpaired d or f electron is responsible for the color in complexes. When there's an unpaired electron, it will get excited in the excited state. Then it realizes, oh, I'm unstable here. I'll jump back to the, it will jump back, not I will not jump. It will jump back to the ground state or some lower energy state where it gives out the extra energy in the form of radiation, which applies in the visible region. We can see that respective color. Fine. Maximum paramagnetism observed in ND, as mentioned here or as given in the books also, due to spin as well as orbital motion of the electron. Spin motion, when the electron spins around its own axis, it creates a magnetic moment. When it rotates around the nucleus, a magnetic moment is created. But for our ease, or I don't know for what reason, when we study n into n plus 2 under root Bohr magneton, we just study about spin only magnetic moment. We study about spin only magnetic moment. It has been found out in ND. It's highly paramagnetic because of spin as well as orbital contribution. Knowing that fact would be good enough. What will be FF transition? Unpaired F. We go get excited, we'll come back to some ground or maybe some lower energy state. And in doing so, it'll give off excess energy. If that radiation lies in the visible wavelength, that region, then only we can see the color. Now, students, if you have 4FN configuration, say 5, 14 minus 5, because when you place them, the number of unpaired electrons here also 14, no, 1, 2, 3, 4, 5, 6, 7, 8, 9. So 4f9 also has 5 valence, or I'm sorry, valence, 5 unpaired electrons. Since both have same number of unpaired electrons, they will show similar color. GD is a ferromagnetic substance. Yesterday we saw what's a ferromagnetic substance. Remember GD? Ferromagnetic substance Nd, highly paramagnetic. Nd, here only. Highest paramagnetism, combined effect of spin and orbital motion is when the electron revolves around the nucleus. The phenomena which is responsible for change of seasons like this. Day and night phenomena, spinning of axis. So these two combined effect, um, very high degree of paramagnetism is exhibited. Gd is a ferromagnetic substance. Yes, here you have to remember lanthanum form Ln2. And in general, Ln is written. Who will write 1 1 again separately like that? Since they show plus 3 as the most stable oxidation state and most common also, so lanthanides will burn in oxygen to form Ln2O3. With acids, it will liberate hydrogen. With halogens, LNX3 will be formed. With water, lanthanum hydroxide and hydrogen will be liberated. With carbon, LnC2 will be formed. And LnN, nitride, will be formed with nitrogen. Sulfides with sulfur. Simple. Mish metal. It will come in the next slide. They ask such questions. Previous years, you see, NEET, plus 8 level. It contains 95% lanthanoids and 5% Fe. That's the reason. It is important. Yes, lanthanoids have a tendency to form alloys. Lanthanides are metals, right? So, 95% lanthanides, 5% Fe. Remember, mish metal. And when it's combined with magnesium based alloy, it will be used in the manufacture of bullets. Mish metal, I've seen questions. Remember, 95% lanthanoids and 5% Fe. Lanthanides can form alloys. Who is coming? Actinides. Now, very similar. I remember uranium 92, Neptune. Okay, a few I know because for radioactivity sake we have to learn. The entire list comes. I saw a lot of anomalous behavior in its electronic configuration. Let's see if we can sum up anything or not. Yes, let's see. So 7s should be first filled because its n plus l value is 7, followed by 5f, n plus l value is 8, and then 60. You'll agree with this? It should be 5f first and then 60. This is following good. Good. Not following. Not following. Not following. Not following. The explanation given in the text is not much energy differences there between 5f and 6s, and hence this anomaly. At least a 5f. Oh, this is also nothing in 5f and directly into 5 6d. Lot of anomalous behavior is seen, and as I read and written here also in the slides, the energy difference between 5f and 60 is very less. Hence, here we understand. Here we understand. Because instead of 5f8, it's better 7 plus 1. Half filled configuration, so it's tick. We understand. Half filled configuration, and we understand. But here, we don't. A lot of such stuff is seen in actinides. Good, good, very good, very good. Excellent. Good people they are. Everyone, did you follow? Why did I say very good? After 7s, it should be 5f and then 60. And these people are following, and this after 5f it's 60. Justified. So not many One, two, three, four. And this one understood. Understood. Anomalous, but understood. A chromium copper. Easy, no? Not that difficult. If we actually analyze,
Yes, ma'am.
yes. Anything you can always let me know. Students, just like lanthanide contraction, there is actinide contraction. Ionic sizes also you will see a regular decrease. Actinide contraction is due to the poor shielding of pi electrons. Color, similar logic. Oxidation state, though you see plus 4, plus 5, plus 6. And basically, no, due to very less difference between this, 5F and 60. 7S, 5F, 60. Not much difference. 7S, then 5F, then 60, increasing order. But because of not that much of difference in energy, you can see multiple oxidation states in the case of actinides. Clustering being most common, you can see plus 4 and plus 5 and plus 6 also. And because of this reason, since they can show variable and as well as multiple oxidation states, they can form complexes very easily. Except promethium. All of the lanthanides are non-radioactive, whereas all actinides are radioactive in nature. As compared to the lanthanides, the hydroxides and oxides of actinides are more basic. GD most, GD ferromagnetic, ND most paramagnetic. 4F5 and 4F9 will have same color. Color is due to FF transitions. In D block, DD transitions except K104, K2Cr27 charge transfer complexes. Wherever you see that they don't have any valence electrons in DNF and still showing color, charge transfer complexes. Yes. Fine. I will stop sharing. Give me some time. I'm here. You can see me 1 minute. Yes. All of the chapters done, no? Don't worry about DNF block. Immediately, if I ask you a question, see, facts are very less. You saw the first 4 5 members like thorium, only cerium there, gadolinium or thorium, and after thorium 90, 91, 92, 93, violating the electronic configuration and all things. Basic nature decreases from lanthanum hydroxide to lutetium hydroxide. Oxides and hydroxides of actinides are more basic than that of lanthanides. A few facts are there. The same thing if I immediately ask. You can tell me the same thing. But if I give you some gap and then ask things, like suddenly I asked an organic question or a physical chemistry and factor or something, then it makes more sense. That's the point. So why wait? And why not start coordination compound? Just we'll do something initial and then lunch waiting. After lunch break, we will continue with our discussion. Students, by this week, we will complete coordination. If I'm not wrong, tomorrow we have you have all the sessions with me where it's a very important chapter where we will complete coordination chemistry, but not hurrying. If we need, we'll take Saturday also. But the way you people are cooperating, you and me together, we can complete it. But let's start first, the last chapter. And after that, you'll have your test series and all, right? Simple salt. Only one cation, one anion. Like NaCl. Na plus, Cl minus. K plus Cn minus. Rb plus Cl minus. What is a mixed oxide? Something like Fe3O4, which contains one FeO and one Fe2O3. These salts will completely ionize in aqueous solution and will give the respective tests of the ions. Sorry. Students, addition salts. You take two, I'll show you the video, that will be easy. Two aqueous salt solutions will mix. Generally, what I had prepared once long time back, long time means really long time back, I took equimolar solutions of um, ferrous sulfate and ammonium sulfate. Equimolar solutions. Mixed them, heated them. After some time, allowed them to cool. I got crystals of FeSO4.NH4 whole twice as 4.6H2. What is that, by the way? FeSO4 dot. I took I don't know what molar I took. Law. I took some X molar FeSO4 solution. I took the same X molar ammonium sulfate solution. Very good salt. Very good. And when I mixed their solutions and heated them on cooling, I got a greenish crystals of, yes, its common name is Morse salt. Now, what I did, how does she remember so many years back? I did or not, I don't know. But if I take these crystals and dissolve in water and test for the presence of ferrous, ammonium, sulfate ions, I'll get all positive tests if I do it properly. I'll get positive tests for the presence of sulfate, ammonium, Fe2 plus ion. So when a double salt is dissolved in water, it retains the identity of the ions. But yesterday, what we did, we took, what we took? What did we take? Finally, we got K4, K4 Fe. The final one I remember. What when all we took? We took KCN and help me out. KCN and FeSO4 will do. I can take this. If I don't remember also, logically it's correct. I'll get this, in which again I'll add excess of KCN, such that I get a K4 FeCN6. This, when dissolved in water, will split into the outside ion has no problem, but the inside one will split into bracket one separate, outside one separate, but the individual components inside the bracket have lost their original identity and formed a different substance. Like here, it will not give positive test for Fe2 plus and Cn minus ions. Reason is these ions have lost their individuality and they have become someone else. These ions have lost their own individuality and become someone else. Means the properties of the complex ion is completely different from that of the individual ions it is formed. Got some idea? Now we'll discuss more.
Yes.
But after the lunch break. Can I ask you one simple question meanwhile? You'll scold me if I ask you an organic question because physical chemistry, inorganic also I'm getting good answers. Organic one I didn't get a correct one. Can I ask you a simple question and I'll get the answer after the lunch break, okay? Means you can take your time. Copy this question because right now this I'm not going to upload. I'm going to upload this coordination after 3:15, right? Huh? So I have taken C6. Okay or not? I can give you or not? Because I'm asked to teach some inorganic chapters which are like left. Okay, it's okay. You treat it with, wait, wait. We will make it treat it with HBr. HBr peroxide. That would be good enough. Copy this question. Fine, everyone? Copied? Can I go for my lunch break as you? Yes. But yeah, we'll discuss after the, yeah, in the next session. Thank you all. Bye. Able to follow whatever I'm teaching? No difficulty? Fine? Okay. Then we are here with the last chapter after the break. Bye. Bye for now.
Bye.